Hi, I'm Eliza McDonald, and today I'm going to talk to you about the second law of thermodynamics. So the second law of thermodynamics, in its formal construction, says that in a closed system, entropy is either going to increase or stay the same. And if this doesn't make any sense, that's okay, because all of these words are kind of weird, and you probably haven't heard them in these contexts before. So there's two big things that are hard to understand in this, and the first is closed system. So closed system is any system that you're not doing anything to. So you just sit it in a box or in a space and you don't change anything. You don't fiddle with it, you don't add any energy, you don't even put it in sunlight, because that's a form of energy that a thermodynamic system can use as well. And second is entropy, which is just a fancy physics term for disorganization. So what this is saying in more practical terms is if you take a system and you leave it alone, it's either going to get more disorganized or it's going to stay at the same level of organization. And in thermodynamics, this can be a little hard to understand because we don't have a lot of intuitive understanding of what organization even means in a thermodynamic system. But in a macroscopic system in the real world that we can see and that we have all this intuition about, it's pretty easy. So imagine a cucumber, and a cucumber is a pretty organized vegetable. It's got a defined shape, it's round, it's got seeds, right? It's got an internal structure, it's got skin, it's got flesh, it has a certain taste and scent that are all defining characteristics of a cucumber, and it's very organized. But if you take it and you leave it in the fridge for 2 months and you go away and you don't do anything to it, you just let it sit, you're going to get instead a pile of disgusting glop, right? All of the little bacteria and fungal spores that are on the outside of the cucumber when you put it in are going to start decomposing it, and you'll end up with the products of cucumber decomposition, aka disgusting glop. So the disgusting glop is way less organized than the cucumber because it hasn't got a shape, it hasn't got internal structure. It's not like all of the fungal bacterial products or the fungal decomposition products are over here and the bacterial products are over here. No, it's all kind of intermixed. There's nothing organized about it. So entropy here has increased because the cucumber was organized and the glop is not. So disorganization has increased, or entropy has increased. Now if you take the glop and you put it in the fridge for another couple of months and you wait, it's not going to reassemble itself into a cucumber, right? That would be crazy. How would it ever do that? But it's going to stay as glop, right? The entropy here is going to stay the same because it's already kind of at its maximum level of disorganization. It might move around a little if it wasn't completely done decomposing, but still basically glop. Same level of disorganization. Now on a molecular level, this exact same thing happens, not with the glop. That's pretty much a macroscopic thing, but you will have disorganization increasing. So, in thermodynamics, we like to talk a lot about temperature. And to a physicist, temperature means something slightly different than it does to a chef or a weatherman, or just a person who's normally thinking about temperature. Now, we think of hot and cold as just hot and cold, but in physics, hot means molecules that are moving really, really fast, and cold means molecules that are moving pretty slowly, just kind of idly wandering around. So if you were to take a hot object, say a copper block, and a cold object, say a cold copper block, and leave them in a box together, walk away, close the system, they would tend to end up at about the same temperature, right, over time, because you've got a level of organization in your system to start off with, right? Over here, you've got fast-moving molecules. Over here, you've got slow-moving molecules. And in the center, there's a line, there's this gap. But when you put them in contact with each other and walk away, that motion can change, right? All of the fast molecules run into all of the slow molecules and start to speed them up, and they lose their kinetic energy. And they both end up as kind of mediumly moving molecules. And so this is what it's like on a small scale. And on a large scale, what we see is this hot thing has gotten less hot and this cold thing has gotten less cold. They've both become more even. And this is what entropy looks like if you interpret tiny motions on a large scale. So it's actually a really pretty simple law. It just takes a little bit of, examples and definitions to make it make sense. I've been Eliza McDonald, and it's a pleasure to talk to you. Bye.